So this is what I was just saying. So in the second half of the course, we will be concerned with treating the plasma as a fluid. In other words, treating the plasma without regard to the behavior of the individual particles, treating the plasma as a fluid which is made up, which is essentially an aggregate of lots and lots of particles. So an individual particle has no identity. Okay, so that is where you will draw most on your knowledge of equations of mass, momentum, continuity in the fluid context. Okay, and this kind of description is what's called magnetohydrodynamics. So hydrodynamics would talk about dynamics of a neutral fluid. Now the reason we say it's not frequently abbreviated as MHD. Okay, the reason we call it magnetohydrodynamics is, well, we will see. We will see. The point is these particles are not neutral, they are charged. There will be some positive particles, there will be some negative particles. However, on the whole, from a macroscopic point of view, the fluid is not charged, the fluid is uncharged. Okay, the fluid is electrically neutral from a macroscopic point of view. The positive and negative charges cancel each other over macroscopic length scale. So this would be some kind of a macroscopic length scale. Okay, however, the fact that the particles are charged leads to the fact that unlike a neutral gas, which doesn't care about, if you applied an external magnetic field to a neutral gas, it wouldn't care. Okay, the magnetic field will simply do its thing. Or if you were applying a steady magnetic field, it would have no influence on the motion of the gas or its temperature or anything. However, this kind of a fluid which is electrically neutral over a macroscopic length scale, but is yet comprised of the elementary constituents of such a fluid are charged particles, such as, say, for instance, an electron-proton plasma, okay, or an electron-positron plasma. Okay, such a fluid will respond profoundly to magnetic fields. You introduce magnetic fields, and the fluid responds to it, and in various ways, and we will study that. Okay, hence the name magnetohydrodynamics. At any rate, having said all this, this is what we will be doing in the second half of the course. Okay, in the first half of the course, the first half of the course, we will mostly be concerned with distribution functions, I should say. With distribution functions of the charged particles. Okay, not the charged particles themselves. Okay, so let's go back. Let's look at this again. Let's go back to this picture again. Now, what if I do not do this? But what if I take a magnifying glass and magnify things such that I'm unable to still see each individual particle, but I'm able to see, it's kind of a mesoscopic, it's kind of a sort of a mesoscopic description. Okay, it's in between macroscopic which would be the fluid description, and the microscopic which is the individual particle description. Okay, a microscopic description would be one in which you are writing down the equation of motion or whatever for each individual particle. Each individual particle, you're trying to figure out the force on it, and you're trying to write down the equation F equals ma, for instance, for each individual particle. But you see, while that would obviously be the most accurate description, that's a computationally very, very intensive process. Okay, so what you will do, what we will be doing mostly, for most part, in the first half of the course is adopting this kind of an in-between description that's neither microscopic, not so small scale as to focus on each individual particle, but also not so large scale as to focus only on the mean properties of an aggregate of particles, such as density, velocity, and things like this. It's an in-between kind of description where we are concerned with distribution functions. Okay, so for instance, a Maxwell-Boltzmann distribution would be one such distribution function. You have velocity here and the distribution function here, and it looks something like that. Okay, so we are actually focusing on the probabilistic distribution function without being concerned only with the mean, which is what a fluid description will be concerned with. Okay, so that's what we'll be doing in the first half of the course. We will be and then to some extent we will also be addressing individual particles. Okay, so that is what is traditionally kind of called plasma physics. For some reason, this is kind of a historical divide. Okay, when you talk about distribution functions and such, it's i.e. the mesoscopic description, it's called plasma physics. And when you talk about the fluid description, it's called magnetohydrodynamics. But mind you, are all descriptions of the same thing. Okay, just at different, shall we say, different resolutions, if you will, or different levels of detail. Okay, this would be a magnetohydrodynamic description, would be the coarsest level of detail. A plasma description, which would focus on the distribution function, is kind of an in-between, a mesoscopic, neither macroscopic nor microscopic. It would be an in-between level of detail. Okay, so this is what we will be doing. Sometimes a plasma physics course is taught in the reverse order. The fluid part is taught first, and then the plasma part. I prefer to do it this way. There's another reason for doing it. In my experience in ICER, there are several students who come into a plasma physics course not having done the fluids course earlier. So this just gives them a little more time, okay, to pick up the basics of fluids, because it's only done in the second half. But of course, all of this assumes that you are keeping up with the class. In fact, you're keeping ahead of the class. Only then, all of this, you derive all of these advantages. Okay, so all of this, when we talk about collisions, when we talk about collective effects meaning effects of not just one particle or two particles, effects pertaining to a bunch of particles which make up the distribution function. Okay, we will talk about something called Debye shielding. Remember I told you that the plasma is essentially quasi-neutral. Well, that depends upon what resolution you go. Of course, obviously, for instance, if you focus on each individual particle, each individual particle is either positive or negative, right? But it turns out that if you go out to sufficiently large distances, you'll have so many positives and negatives that, you know, over a macroscopic length scale, the net charge is neutral. There's a little more to it than that. It's the fact that suppose you have a positive charge here, okay, and positive charges are almost always heavy. For instance, if you think about an electron-proton plasma, the proton is 2,000 times heavier than electrons, right? So the moment you place a positive, the moment you place a charged proton here, there will be, you know, the very light mobile electrons will immediately rush in and form a little cloud around it, a little electron cloud around it, effectively shielding the positive charge. So turns out that if beyond some kind of a distance, okay, you will not feel the influence of the positive charge anymore. And this is what's called Debye shielding. Okay, and then we'll talk about something called the plasma parameter, so on and so forth. Okay, and then we'll talk a little bit about orbit theory. And here we are focusing on individual particles. Okay, yeah. So here we will focus on, like I said, we will be doing a little bit individual particles. Okay, mostly high energy particles. Okay, so you will have a background plasma, but comprise, say some kind of characterized by some kind of a temperature. But oftentimes is the case that in the midst of this background plasma, you will have a few high energy particles, charged particles. Okay, and in order to follow the dynamics of those individual particles, you need to, you know, follow them individually. Okay, the density of those high energy particles is not high enough to consider them as definitely as a fluid, and even as a distribution function. So you would have to follow those individual particles around, and in order to do that, you would have to do something called orbit theory. This is the part of the course that you'll find I don't want to say easiest, but most familiar from your basic electrodynamics background. Okay, and this has got lots of very important applications to tokamaks and to particle motion in the Earth's magnetic field, and so on and so forth. And this is covered in chapter 2 of Boyd and Sanderson and chapters 3, 4, 5 of Sturrock. Now, one other thing I wanted to emphasize as we go along is that although I'm pointing you to these chapters, by no means I'm going to cover all the material that's in these chapters. You see, chapters 3, 4, 5, there's no way I'm going to be covering all the material in these chapters. I pick and choose, okay, what I consider to be the key elements, okay? And so that's what I will be presenting in these lectures. And it's up to you to follow these lectures and then go back to the book and read the rest of it. Okay, and try to see, and that will give you a feel for how much more there is. Okay, so just to emphasize that when I say I'll be taking this from chapter 2 or taking this from chapter 4 or whatever, I will only be, cherry picking. I'll only be picking and choosing elements from these chapters. Okay, right. The second module is still plasma physics. Okay. But we will be talking about waves in plasmas. Waves in cold plasmas, waves in warm plasmas, so on and so forth. So these will include the familiar light wave, By light wave, I simply mean waves that you've studied in electrodynamics, in standard electrodynamics, waves in vacuum. Okay, the transverse waves. which propagate at the speed of light. So this will include the familiar light wave. But because now we are not talking about vacuum, we are talking about a plasma, we're talking about a medium. Okay, it turns out that the presence of a medium means that there's a whole bunch of other waves that wave solutions that are allowed. Okay, so in addition to the familiar electrodynamic wave, you have a whole bunch of other waves, and these are very important because what are waves after all? Just disturbances, right? And so it's important to understand how disturbances propagate in a medium, right? And we will talk a little bit about collisions in plasmas. And module 3, which by module 3, we are, by the time we get to module 3, we are entering the second half of the course. And that is where we will start talking about the macroscopic fluid description of the plasma, as we discussed. And in this, we will be covering the equations of magnetohydrodynamics. We will also talk about waves in the magnetohydrodynamic description. Okay, you can talk about waves in the distribution function description, or in what's often called the plasma description. And when you coarse grain the situation so that you're studying magnetohydrodynamics now, there's a whole different kind of a different zoo of waves that appear. Okay, so we will study waves in magnetohydrodynamics, and these are the references. Let's see, right. And the fourth module is the applications module, and I will, since I do astrophysics, in particular astrophysics with a plasma physics bent, I'm more comfortable with talking about astrophysical applications such as the solar dynamo, the way in which magnetic fields are produced in the sun. From the solar interior, jets from accretion disk systems, accretion disks around black holes, exotic objects like that. And I will also try to say something about applications to lab applications to fusion plasmas. Okay, or more correctly, I should say applications to lab fusion plasmas that are produced in the lab. Okay, so that was the lay of the land, so to speak. And so let us get into the course. Let us get into module 1 now. So you see, lab plasmas, mostly by way of applications to thermonuclear fusion, are of great interest as a clean, green, and relatively risk-free energy source. Nuclear fission, energy from nuclear fission is also, they also tick these two boxes, but relatively speaking, they are much more risky than generating energy via thermonuclear fusion. Okay, there's always the risk of runaway fission and well, okay, even though there's a lot of effort devoted towards ensuring safety, it's generally acknowledged that nuclear fission is a somewhat more risky energy source. Okay, the problem with nuclear fusion is that you need to essentially what you're doing is you're trying to replicate the conditions at the core of the sun. Okay, so you're trying to confine plasma at very high density, at high enough densities and temperatures such that hydrogen fuses into helium. But the main issue is confining. It's just this thing, just confinement. Okay, so confining a plasma is a difficult thing. In particular, confining it for long enough for fusion to occur. Because the plasma is a jiggly wiggly thing. It doesn't like to be confined, and it's subject to a whole host of instabilities. And by the time you're trying to confine it, it just breaks loose and spatters on the walls of your container, and the plasma state is lost. So it cools off, and you cannot achieve fusion. This is very roughly speaking, the biggest challenge for thermonuclear fusion. Okay. The other part of the motivation, of course, is that, space or an astrophysical plasma, some 95% of quote-unquote space is not empty. Okay, this is the other thing I wanted to. Space is not empty. Okay, no such thing as vacuum. There's just very, very thin, very tenuous plasma in space. In fact, about 95% of space is plasma. Okay, so say you're studying astrophysics and you're trying to, understand understand the behavior of some very far away object like a pulsar or something. So what you're observing is photons from this distant object. You see, but these photons are not simply traveling through vacuum. They are traveling through a medium, a very thin medium. Okay, it's very thin, but it's not completely empty. Okay, it comprises charged electrons, protons, and charged particles of other species also. Okay, other nuclei, for instance. And the fact that this intervening medium between you and the object is not quote unquote empty. It's in fact comprised of plasma. Makes a big difference to the propagation of these photons. The photons are propagating through this medium, and the medium changes the characteristics of the photon. For instance, affects its polarization. If it's a small pulse, it disperses it, so on and so forth. Okay. So what you're observing is a convolution of the properties of the source as well as those of the intervening medium. So you need to understand the properties of the intervening medium very well if you're to understand, if you're to make some deductions about the source from which these photons are coming from. Okay, so you can say that's one of the broad motivations for studying plasmas in the astrophysical context. So you see, all electromagnetic radiation from cosmic sources propagate through a plasma. Okay, and so you need to understand the properties of the plasma to understand how the radiation is affected by the fact that it propagates through the plasma. Okay, right. And roughly speaking, you can think of plasma as quote unquote ionized gas. Okay, so in other words, the gas is not neutral, the gas is ionized. It's not just neutral hydrogen, it's ionized hydrogen. Okay, protons and electrons separately. Okay, so in addition to whatever properties a gas exhibits, okay, it's also profoundly influenced by electric and magnetic fields, simply because it's ionized, simply because the elementary constituents of this gas are particles, are charged particles, ionized particles. Okay, and as we will see, it's mostly influenced by magnetic fields, not electric fields. That arises from the fact that the plasma taken as a whole is charge neutral. Okay, but roughly speaking, this is how you can think of a plasma. Okay, and but to start with, what we will do, and we will take this up in the next lecture. We will briefly review some properties having to do with gases or fluids. What we will do is review things like what do you mean by particle density of a gas? What do you mean by temperature of a gas? Where did this come from? So these kinds of things. These are essentially, I would say, basics from kinetic theory. So we will start with this in the next lecture.